Ever wondered how object-oriented programming works in Java? Well, you're in the right place. Object-oriented programming, or OOP for short, is a programming paradigm that uses objects and their interactions to design applications and computer programs. It's like the building blocks of Java and really any other object-oriented language out there. Now, there are four main OOP concepts in Java. First, we have inheritance, which allows one class to inherit the features of another, creating a parent-child relationship of sorts. Then there's encapsulation, which bundles data and methods that act on that data into a single unit. Next, we have polymorphism, enabling us to perform a single action in many different ways. And finally, there's abstraction, which hides the implementation details and shows only functionality to the user. These concepts are the backbone of Java programming. So buckle up, as we're about to dive deeper and understand each of these concepts one by one. First up, we have inheritance. Now, what's that all about? Well, in Java, inheritance is a mechanism that allows one class to inherit or take on the features of another class. This might sound a bit abstract, but let's demystify it with a simple example. Imagine you're creating a program about animals. You start by defining a generic animal class which has a method called eat. This method, when called, simply prints out the phrase eating. Now, this is a behavior that all animals share, right? They all need to eat. But what if you want to introduce more specific animals into your program, like a dog? You could create a new dog class and define the eat method all over again. But that's unnecessary repetition. This is where inheritance comes into play. Instead of rewriting the eat method, you can simply have the dog class inherit from the animal class. This is done by using the extends keyword in Java. So your dog class declaration would look like this: class dog extends animal. Now your dog class automatically has the eat method, even though you didn't explicitly define it in the dog class itself. That's because it inherited this method from the animal class. But dogs don't just eat, they also bark. So in the dog class, you can define a new method called bark. This method, when called, prints out the phrase barking. And there you have it. You've successfully used inheritance to create a dog class that has both eat and bark methods, without having to rewrite the eat method. This is a prime example of reusability, one of the main advantages of inheritance. Inheritance isn't limited to just methods, though. It can also be used to inherit properties or variables from a superclass. But that's a topic for another day. For now, just remember this. Inheritance is all about taking what's already there and building upon it. It's about standing on the shoulders of giants, or in this case, standing on the shoulders of superclasses. That's inheritance for you. It's all about reusing code. Next in line is encapsulation. This is one of the four pillars of object-oriented programming in Java, and it's all about data protection and integrity. But what does that mean? Let's break it down. Imagine you're a bank, and you've got a vault full of gold. You wouldn't just leave that gold lying around for anyone to pick up and walk away with, right? You'd want to protect it, keep it secure. That's what encapsulation does for your data. In Java, encapsulation is a mechanism that allows us to wrap our data, which are our variables and the code that acts on this data, our methods, together as a single unit. This single unit, or capsule, if you will, hides the data from other classes. It's like our bank vault hiding our gold from the outside world. But of course, we still need to be able to access and interact with our gold, right? And the same goes for our data. In encapsulation, the variables of a class can be accessed only through the methods of their current class. These methods are like our bank tellers, the only ones with the authority to get into the vault and handle the gold. For example, consider a class called employee. In this class, we have a private variable name. Now, the only way to access or modify this name variable is through the getName and setName methods within the employee class. This is encapsulation in action. So why is this important? Well, encapsulation gives us control. It allows us to protect our data, to maintain its integrity, and to prevent outside interference. It's like our bank protecting its gold, maintaining its value, and preventing theft. So encapsulation is all about data protection and integrity. It's about keeping our data safe, secure, and controlled. It's about making sure that our data, like our gold, is handled with care and respect. So the next time you're working with Java, remember the power and importance of encapsulation. Always protect your data and it will serve you well. Moving on, we have polymorphism. This term is derived from the Greek words poly, meaning many, and morphs, meaning forms. So essentially, polymorphism in Java is the ability of an object to take on many forms. Now let's illustrate this with an example. Imagine we have a superclass named animal with a method called sound. This method simply outputs a generic message. Animal is making a sound. Now we introduce two subclasses, horse and cat. Both these subclasses inherit from the animal superclass, and they both override the sound method. For the horse, the method outputs neigh, and for the cat, it outputs meow. So what's happening here? We are performing the same action, calling the sound method, but the outcome changes depending on the form of the object. If the object is a horse, we hear a neigh. If it's a cat, we hear a meow. This is polymorphism in action. The same method behaves differently based on the object that invokes it. This feature is incredibly powerful. It allows us to design methods that behave differently for different classes, yet we can invoke these methods in a uniform way. This makes our code more flexible and extensible. If we decide to add a new animal into our code, say a dog, all we need to do is create a dog class, have it inherit from animal, and override the sound method to output woof. There's no need to change any existing code. Polymorphism also supports the concept of interface. An interface is a contract that guarantees certain methods will be present in a class. So, if a class implements an interface, it's guaranteed to have those methods, though the behavior of the methods can be different based on the class. This gives us a way to ensure consistency across different classes. Polymorphism, therefore, gives us flexibility and dynamism. It's a tool that enables us to write more adaptable and maintainable code. It's a key concept in object-oriented programming and a powerful tool in the hands of a skilled programmer. Finally, let's look at abstraction. Abstraction is one of the four main pillars of object-oriented programming in Java. It's a process that helps us focus on what an object does instead of how it does it. It's like looking at a car. You don't need to understand how the engine works to drive it. The internal complexities are hidden and you see only what's necessary. In Java, we achieve abstraction using abstract classes and interfaces. An abstract class is a class that cannot be instantiated. In other words, you cannot create an object from an abstract class. It often contains one or more abstract methods declared without an implementation. Let's illustrate this with an example. Consider an abstract class, shape. This class has an abstract method called draw. Now we have two other classes, rectangle and circle, extending shape. Both these classes provide their own implementation of the draw method. In the rectangle class, the draw method prints drawing rectangle, while in the circle class, it prints drawing circle. When you create a rectangle or circle object and call the draw method, the appropriate message is printed. You don't need to know how the draw method is implemented in either class to use it. This is the power of abstraction. It allows us to hide the internal workings of our classes and expose only what's necessary. By doing this, we can change the internal implementation of our methods without affecting other parts of our code. Imagine if we decided to change how we draw our shapes. As long as we don't change the draw method's signature, we can modify its implementation in the rectangle and circle classes without affecting any code that uses these classes. In essence, abstraction is about hiding complexity and showing simplicity. It's about creating a simple interface that others can use without getting lost in the details. It's a powerful tool in a programmer's toolbox and a cornerstone of object-oriented programming. We have now explored the four main OOP concepts in Java. Let's quickly summarize. First, we dove into inheritance, the concept that allows one class to gain the properties and methods of another, promoting reusability and a logical structure to our code. Next, we tackled encapsulation, the principle of binding together the variables and methods that manipulate the data, and keeping these safe from outside interference and misuse. Then, we turned our attention to polymorphism, the ability of an object to take on many forms, allowing us to perform a single action in different ways. Finally, we looked at abstraction, the process of hiding the complexities and only showing the user what's necessary, making it easier to handle complexity. These pillars of object-oriented programming are not just theory, they are practical tools that guide us in designing robust, flexible, and easy-to-maintain code. Understanding these concepts is crucial for working with languages like Java. Happy coding!